For this video, I'm going to go through my Chapter 9 slides as I would in lecture. And the main reason for that is because Chapter 9, along with 10 and 11, are a whole lot of conceptual ideas, not really involving too much math. And so there's not really much I can do on the whiteboard, but there's a lot of stuff I can kind of discuss along with my slides. So I'm going to be going over the same slide set that you all have access to on Blackboard. So if you want to kind of follow along with your slides as I'm going through my slides, it might actually kind of benefit you. And so the first idea that we're going to discuss for Chapter 9 is why even create these bonds? And so when we start talking about, mainly again, talking about ionic complexes, for now we're going to talk about ionic stuff. Later on we'll kind of get into the covalent bonds. But as far as ions are concerned, once you remove an electron or add an electron to an atom, sometimes again it might be a good thing that sodium becomes a positive ion and chlorine becomes a negative ion. But as soon as that happens, Mother Nature gets really aggravated whenever things are not equal or when things are not balanced out. And so in these cases, whenever you form an ionic bond, it is mainly because a positive ion and a negative ion by themselves are not stable. And so as soon as they have this positive or negative charge associated with them, in order for them to become stable, they will kind of connect, or they'll kind of come close to each other and form what we refer to as an ionic bond. And so the main reason why you're going to form a bond is because it always lowers the energy of these atoms. It makes everything, like nature in itself, more stable than it would have been if they were completely separated from one another. And so how they bond, we've discussed these in previous chapters, but basically if you have a metal and a non-metal come together, you're going to be looking at ionic bonding. Whenever you have a non-metal with another non-metal, you're going to be forming covalent bonds. And so we've discussed these concepts in the past, but now again we're really going to get into why these things happen and how these things happen. And so in the past I've told you certain things like oxygen always has two lone pairs on it, and you've kind of nodded your head and said yes. But now in these next 3 chapters we're going to get into why these things actually occur the way they do. And so before we get any further, we have to talk about these, or what they're referred to as Lewis dot structures, or Lewis dot or electron dot structures. They go by a couple different names. The main idea is you're going to be looking at these atoms in reference to how many valence electrons they have. And so most of the time we're going to be sticking with the main group elements. We're going to stay away from the transition metals for now, well at least until Gen Chem 2. And so if you are looking at the main group elements, the easiest way you can kind of go about this is the number of valence electrons is the group number that that element is sitting in. And so for instance, if we want to talk about something like nitrogen, if you bust out your periodic table and look for N on the periodic table, you'll notice it's in group 5. And so you start off by writing down the chemical symbol for your nitrogen, or Rn. And again, using the periodic table, we can see that nitrogen is in group 5. That means that nitrogen is going to have 5 valence electrons, and we need to, I guess, kind of display these as dots around nitrogen. And so for nitrogen, it's kind of easy to kind of tell what I mean by a square or by a round. But for here in nitrogen, just kind of picture a square around nitrogen, and so it has 4 sides, top, to the right, to the bottom, and to the left. And so same deal with oxygen. I know oxygen is O and O is round, but just kind of picture a box around the oxygen. And so knowing how many dots you need to draw, you draw 1 dot around your nitrogen, or 1 dot each around each side, and make sure that each side of your nitrogen has 1 to begin with. After that, then you can kind of start doubling up on your dots or doubling up on your sides. And so here I have drawn 4 dots around nitrogen, but as I stated, nitrogen is group 5, so we need 5 dots. And so just because of a matter of opinion, I like to put them on top first, and so I can put my 5th dot on the top side, or top area. But it doesn't really matter at this point, mainly because this isn't real. And so you have to remember that when we draw these things, we are drawing them in 2 dimensions because we can't draw in 3 dimensions as of right now. And so when we draw these Lewis dot structures, the thing you always have to keep in the back of your mind is that these are fake. These are just going to be general guidelines in order to kind of estimate how all this stuff is connected. But as soon as they go from 2 dimension to 3 dimensions, as you'll see in chapter 10, these things actually do not exist in any way that we're drawing them for the most part. And so in order to kind of keep things clear here, in order to make you all feel better, if you want to draw your 2 dots on the right instead of the top, go for it, because this is the same as exactly what I had drawn previously. Or maybe you feel like you want to draw them on this side or even on the bottom. It doesn't really matter at this point in time. As long as you have 5 dots around your chemical symbol, you have a Lewis dot symbol or a Lewis dot structure. And so, when we go from our Lewis symbols, we can again kind of start inferring how many bonds these things are going to be creating and even how they are going to form those bonds. And so, general guidelines when you kind of draw these Lewis symbols is if you are dealing with a metal, and again, typically we're going to be dealing with just the main group elements. So the metals or those group 1 and group 2 elements are going to lose their electrons. Metals will always form cations. That's just the way that they are. And so in these instances, the number of dots is going to equal the number of electrons that the atom will lose in order to form a cation. Please note, I am talking about metals. I am not talking about non-metals yet. And so for metals, the number of dots you're going to draw around the symbol is going to be the number of electrons that that atom is going to lose in order to form a cation, such as sodium in group 1. Because it's in group 1, we know that sodium is going to have a common ionic charge of +1. The reason why it's a +1 is because it loses 1 electron. And so when we draw these things out, sodium is going to have 1 valence electron, or therefore it's going to have 1 dot on its Lewis symbol. Additionally, magnesium is in group 2, and so we know that magnesium is going to have a common ionic charge of +2. Again, reason for this is because magnesium loses 2 electrons to form a 2+ ion. So therefore, group 2 means you have 2 valence electrons. Magnesium loses its 2 valence electrons, and so we're going to draw magnesium with 2 dots. Please note here I have dots on either side of magnesium because you are not going to put both dots on one side of magnesium until every side has its dots around it. And so non-metals on the other hand, or again, things on the other side of the periodic table, or things in groups 3, 4, 5, 6, and 7, the non-metals are going to have the number of dots is going to be different than the number of dots for the metals. And so one way of kind of looking at this for your non-metals, again, in general, you're going to draw the number of dots of the group number or the valence electrons. But say you don't have a periodic table handy, but you have these charges associated with them. And so the non-metals, the number of unpaired, and please note, unpaired dots is going to be the number of electrons the atom gains to form an anion, or it's going to be the number of electrons that it's going to share to form a covalent bond. One more time, nonmetals can be in both ionic complexes as well as covalent complexes. And so in your ionic complexes, the number of unpaired dots is the number of electrons the atom is going to gain. In your covalent bonds, the number of unpaired dots is going to be the number it shares to form that covalent bond. And so for instance, chlorine is in group 7. We know that because it's in group 7, it's going to have 7 valence electrons. So therefore, in order to fill up its octet, that chlorine is going to want to gain 1 electron to form a 1 negative ionic charge. And so in this instance, we know that your chlorine is going to have 7 dots around it. In addition to the rule I just stated, and in its ionic form, we know that chlorine is going to have 1 unpaired dot. And again, 7 valence electrons, 7 dots. Just to confirm everything I just stated is true, if we have a -1 ion, that means it's going to want to gain 1 electron, therefore it needs to have 1 unpaired dot. And so in the future slides, you'll see why this 1 unpaired dot matters. And so this is again for your ionic charges. Let's say that we want to talk about chlorine in a covalent form. And so in this instance, again, chlorine is still going to have one electron being shared, not gained or lost, but shared when forming covalent bonds. And so here, again, I have chlorine and bromine, so you can kind of see the difference here. But chlorine and bromine are both halogens, meaning they both have 7 valence electrons. And so when they form a covalent bond, chlorine is going to share one electron, bromine is going to share one electron in order to form that covalent bond between the two. And so I've kind of touched on this in the previous chapters, but again, the octet rule states that main group elements are going to want to lose or gain or share electrons in order to obtain a outer shell electron that is completely filled. Outer shell electrons are completely filled. And so there are exceptions, hydrogen and lithium, only because they just have one s. You can't fit 8 electrons into a 1s orbital. But for most of the other elements on the periodic table, this is why all these elements really want to be like the noble gases. The noble gases have S2p6, or filled outer electron shell. And so in these cases, the octet rule states that everybody wants to have 8 electrons or 8 dots surrounding them if at all possible. And so if we kind of go through the periodic table and just looking at at periods 2 and 3, in group 1 we know it has 1 valence electron, so we're going to have 1 dot. Group 2 we're going to have 2 valence electrons, so we're going to have 2 dots. Groups 3 and 4, you see kind of where I'm going here. But the main thing that you need to get across from this slide is that you need to have 1 dot per side before you start doubling up. So please notice on carbon, on silicon, they have 4 dots, but none of those dots have, or I guess none of those spaces have 2 dots yet. It's not until nitrogen and phosphorus where you actually start doubling up, where you have 5 and 6 and so on and so forth in terms of electrons. And so, I've talked about ionic bonding so much, but one thing you have to kind of understand is you can illustrate how these things form ionic bonds in a couple different ways. We've kind of talked about in the last even like 3 chapters, 3 different ways that we can illustrate how these electrons are going to be bouncing around. And so one thing you have to remember is ionic bonds is whenever electrons are being transferred, completely transferred from a non-metal to other way around. When electrons are being transferred from a metal to a non-metal. And so in these cases, as soon as that electron is being transferred, you have ions form. As I stated in that first slide, as soon as those ions are formed, they can't exist as a Li plus and F minus, or Ca or Cl minus and Na plus. They have to, again, be attracted to one another in order to lower their energies. And so in these instances, one way that we can kind of look at this is the electronic configurations. And so if you look at the electronic configuration of lithium, again, group 1 element implying that it has 1 valence electron. That 1 valence electron is sitting in your 2s orbital. On the other side, we have fluorine. Fluorine is a halogen sitting in group 7, and so it has 7 valence electrons. But in order to satisfy its octet rule, or for lithium, its duet rule, we know that lithium only wants to have a completely filled 1s orbital, and your fluorine wants to have a completely filled 2s2p orbital. And so in this case, you have to kind of ask yourself kind of a general question. Would it be easier for lithium to get rid of that 1 extra electron sitting in that 2s? Or will it actually be easier for that lithium to go out and hunt down 7 other electrons? And so here again, that lithium would have a much easier time just kicking out that 1 electron in the 2s and basically, essentially, kind of completely destroying that 2s orbital. And so on the other end, fluorine. Fluorine, would it be easier because again, it has 7 out of the 8 electrons. Would it be easier for fluorine to find 1 electron or to kick out 7 electrons out of or n equals 2? And so here again, should be easy to kind of guess. Your lithium is going to be, it's going to be easier for lithium to kick out 1 electron. It's going to be easier for fluorine to grab a hold of 1 electron. And so in these instances, your lithium will be more than happy to give up its 2s electron fluorine would be more than happy to accept that electron. And so in these instances, you create your lithium, or again, 1s2, which is a filled outer shell. Then you have your fluorine minus, which again, 2s2, 2p6, filled outer shell. So both of these are going to be much more stable and satisfied. And so another way we can look at this is if we look at our orbital diagrams. And so in the orbital diagram, same information is being displayed, but now we're looking at arrows instead of numbers. But here again, you can see that it's going to be a lot easier for that lithium to kick out that electron in the 2s orbital because it has 7 out of those 8 spots unfilled. And so it's going to be way too much energy and too much work to spend in order to fill up all 8 of those spots. And so again, lithium would be more than happy just to kind of shut down all of the n equals 2 and be at 1s2. Fluorine, on the other hand, has one spot, one tiny little arrow that it needs in order to have a completely filled 1s2, 2s2, 2p6. And so in this case, as before, the one electron from the 2s orbital in lithium jumps ship and it goes over to the 2p6 for fluorine. And so as soon as that happens, lithium is happy with its 1s2, fluorine is happy with its 2s2, 2p6. And one more time, now that we have Lewis dot symbols, we can see the same information, but now we're looking at dots instead of arrows, instead of numbers. And so here again, lithium has one valence electron sitting out there. It'd much rather have all of them or none of them sitting there. So in this case, your lithium dot will jump over and become a fluorine dot. And so this again, the lithium, the 2 dots I'm showing on the right now, they just come from the 1s2. And so I'm just trying to illustrate, again, lithium is one of the ones that it does not have an octet. It can only get like 2 electrons maximum because it only has the 1s sitting there. But fluorine, you can see fluorine's nice and happy because it's 8 dots around it. And so in these cases, 3 ways of illustrating the exact same concept. If you gain electrons, lose electrons, the main reason why you're going to do that is to satisfy the octet. But as soon as you satisfy the octet, then you're going to have ions. Ions just inherently, and again, more information about this on these coming up slides, are going to be attracted to each other because it releases a whole buttload of energy, and therefore it becomes a much more stable environment. So far I've talked about one electrons kind of jumping back and forth and everything. So let's move on and see what happens if we have more than one situation kind of going on here. And so say I want you to combine the sodium plus ion and an oxygen 2 minus ion. And so if we use the Lewis symbols again, because sodium is a plus, we know it has 1 dot. Because oxygen is a 2 minus, we know that it has 2 unpaired dots. And so just using that information without a periodic table, we know we can draw this sodium with 1 dot and oxygen with 6 dots. Because remember, for your anions, for your nonmetals, the number of dots, the number of unpaired dots is the number of electrons it's going to either gain or share in order to create these compounds. And so here, if you know that sodium, much more stable if it gets rid of that 1 dot. Oxygen, much more stable if it hunts down 2 dots. And so sodium can kind of give up one of its electrons in order to oxygen. But if we take a look at what we have here, sodium is fine. It got rid of its 1 dot, and so it went down to its previous layer and it's sitting at S2P6. But the oxygen, it still has an issue. And so as soon as you give 1 dot to oxygen, we're still sitting at 7 out of 8 dots. And so the easiest way to fix this, if we're still talking about a combination of sodium and oxygens, is just use another sodium. And so in here, another sodium can come in with another dot and it can satisfy this octet here. And so now we're looking at Na2O, and this is the reason why you have to have 2 sodiums for every 1 oxygen. This is why you have to have 2 of your pluses for every 1 of your 2 minuses. And so same idea if we have arrows instead of dots. But again, in this case, we have our sodium is going to be 3s1, or illustrated by that 1 arrow in that 3s orbital and nothing in the 3p's. And if we add this to oxygen, Here again, your oxygen is at 2s2, 2p4, and it's missing those last two arrows to satisfy everybody's octet. So same kind of deal applies. The first sodium will give up its one electron, and that electron will go into that second 2p orbital. The second sodium will give up its one electron, and that electron will go into that last 2p orbital. And so in these cases, again, your sodium will completely shut down its n equals 3 orbitals in order to become 2s2, 2p6. Your oxygen will now gain 2 electrons and now have a completely filled outer orbital. And again, the outer shell is going to be 2s2, 2p6. And so here, both of these, or I guess in all essence, all three of these atoms gain or lose their electrons to end up with an electronic configuration of 1s2, 2s2, 2p6. Again, sodium plus and oxygen 2 minus have the exact same electron configuration. But because it is the electronic configuration of a noble gas, it means everything's much more stable than it would have been if they were just their atoms by themselves. And so, this next idea I have to kind of talk about can be very confusing if you look at this diagram in your book without having some kind of basic understanding of what you're looking at. And so the main idea you have to get across is it takes a whole lot of energy in order to set everything up properly. But because, again, of the inherent issues I talked about in the past of opposite charges attracting each other, this energy that you have to spend in order to set everything up is well worth it, and you get a huge payback or a huge release of energy at the end. And so one thing I have to warn you about here, and the reason why I kind of have things colored in red and green, is because you have to remember something about your delta H's, or about your enthalpies, and about your heats and everything else. So remember back in the thermochemistry chapter, if you gain energy, that means you have to find it from somewhere else. And so whenever I start talking about these chemical reactions or even like chemical steps, you have to understand that finding energy is not always a good thing. Because if you don't have the energy to complete the process on your own, it has to come from somewhere else. And so if you're a chemical and you have to break a bond, or if you have to do something, you can't do that by yourself. That means that heat has to come in, or somebody has to shake you, or somebody literally has to go in there and break that bond. And so whenever I talk about cost or energy cost, I mean you have to have it come in from somewhere else. But whenever I talk about energy release, again, releasing energy is the whole point of this chapter. If you want to, or when you make a bond, it's because you are releasing energy, becoming more stable. So releasing energy, good, that's what we want. Absorbing energy, not really a good thing, because that energy has to come from somewhere. And so the easiest analogy I can kind of think about in order to relate this to chemistry-wise and money, because we all understand money, is if your buddy comes up to you and says, hey, I have a great investment, you just need to give me $500 and I will give you $1,500 next week. And so in this case, yeah, $500 is a lot of money, but to get back 300 or like threefold at the end, it's also a pretty good payback. And so the whole idea can kind of be summed up in these next couple steps. And so please just understand, I'm just taking this one step at a time. We have discussed all of these ideas in the past. I'm just now applying them to just one overall concept. So the first thing we're going to talk about is lithium fluoride. And so whenever we form lithium fluoride, from our minds as human beings, we're kind of arrogant in the fact that we are very kind of quick-minded. If we mix lithium and fluorine, hey, we got lithium fluoride, we go about our lives not giving it a second thought. But if we're an electron, there's a lot of stuff that's happening in order to kind of get these things in the right order. And so when we kind of talk about lithium fluoride, as I kind of put here in my blue font with a purple background or purple box around it, you need to remember your sign convention. As I mentioned, absorbing energy is not always a good thing. And again, you have to find the energy from somewhere else. And if you can't get the energy from somewhere else, it's not going to happen. And so these first few steps, whenever I have it in red, the value is going to be positive. But remember, for an electron, positive numbers are not a good thing, because you have to get that energy from somewhere else, and it doesn't happen just because you want it to. And so the first thing we have to kind of talk about is lithium. And so lithium is a metal, and it is a very reactive metal. And so lithium is not just going to spontaneously combust and become a gas. And so in this instance, if we kind of talk about lithium as a solid, you have to understand, or remember at least, that solid atoms are completely condensed. They are touching one another. And so if you want this lithium in some form that you can actually react it with fluorine, you need some space between all those atoms. And so all I really mean here is whenever I say lithium is going to be transformed into gas, you normally don't come across lithium gas. And the reason for that is because lithium doesn't want to be a gas. It wants to be a solid. And so in these cases, if I'm telling you lithium is in gas, it doesn't happen just every other day. In order to do so, you have to put energy into the system. You have to have your solid lithium, and you have to beat the heck out of it in order to separate those atoms far enough from one another that it is no longer a solid. And so in these cases, again, it's going to have to absorb 161 kilojoules of energy for every 1 mole of solid lithium. And so one thing we kind of talked about in the past is that this is just delta H. This is the energy required for this reaction to occur. And so the other thing is, as soon as we have lithium in a gaseous state, lithium itself is not going to do us any bit of good. Because as I kind of covered in the previous steps, we're talking about an ionic complex. And if it's an ionic complex, that means we need to have lithium in its ionic form. And so for this instance, again, we're going to take our lithium gas and we need to convert it into a lithium ion. And so as we've kind of covered in previous chapters, lithium is going to lose 1 electron in order to become a lithium plus ion. And so as soon as that happens, again, lithium is going to have to absorb energy in order to get that electron knocked off. And so some of you may recall and may be asking yourself the question about, again, this ionization energy. And so the ionization energy for lithium is relatively low. Again, lithium will have no problem kind of helping you out and get rid of that extra electron. But it still requires some energy to actually pull that electron off. And so kind of think about this as, even though lithium will get rid of, lose that electron relatively easy compared to a lot of the other elements on the periodic table, you still have to go and find your magnifying glass. You still have to go and get your tiniest pair of tweezers ever, and you actually have to pluck that 1 electron off. Meaning the fact you as a person have to do work onto that atom in order to get this process completed. And so the ionization energy, or the energy required for you to remove 1 mole of valence electrons from 1 mole of gaseous lithium, is going to be 520 kilojoules. Again, absorbed energy, not really a good thing for these atoms to do. So now we have lithium ions. The other half of this is going to be our fluorine ions. And so fluorine, luckily for us, is a diatomic gas. And so there's a lot of space between these atoms in the gas, and so we really don't have to do the same thing like we did with lithium. We don't have to convert it from a solid to a gas. But the problem with fluorine is F2. It is a diatomic gas. But lithium fluoride, or LiF, only has 1 fluorine in lithium fluoride. And so because of that, we don't want F2. We actually want 2 Fs. And so here, F2 is always a diatomic gas. It's not just going to spontaneously break down into 2 separate Fs. And so again, it has to have energy absorbed, or you as a person have to do something to that F2 in order to break it down into 2 separate Fs. We refer to this as the bond energy. And so it's just saying that you need to, again, or not you, the atom or the diatomic molecule of fluorine has to absorb 79.5 kilojoules of energy in order for that F2 to break down into 2 separate Fs. And so, as I stated before many times, and as I'm probably going to say many more times throughout this video, all these red values, all these positive values, You are a human being. When we see positive values, we think of it as a good thing. Remember, this is a bad thing if you are an atom or an element or electron, because you have to find this energy from somewhere else. You personally do not have the capabilities of carrying out these reactions or these mechanisms or steps because you don't have the energy that's required. And so as with these first three steps, you can kind of see it's not really looking very good for these this electron or this actual transfer going on. And so you can kind of think about this as that big screen TV you really want, but you don't have the money to pay for it, so therefore again it's not going to be your TV quite yet. But luckily for us, the last step on this slide is going to be kind of a turning point. So similarly to what we did with our lithium gas in order to create our lithium plus ion, we took an electron away. But for fluorine, fluorine is a very electronegative atom, like the most electronegative atom. And so as soon as you start dangling that electron in front of an F, like gas, or your fluorine gas, and again F by fluorine, just your fluorine, just a single F. But as soon as you start dangling that electron in front of it, it's going to be more than happy to take that electron. And it's actually so happy that you gave an electron that it's actually going to release energy instead of absorb energy. And so adding that one electron to that F in gaseous state, you are now going to see your first release or your first payback of energy. And so this is referred to as your electron affinity. And so again, whenever you add an electron to an F gas, you're now going to be seeing a release of 328 kilojoules of energy. But if we take a look at these, as I kind of stated, there's a lot of red. And so just considering these first few steps, we're still kind of sitting at 432.5 kilojoules of energy just required to set all this stuff up. And so at this point, you should be asking yourself, what the heck is the point? It's costing way more energy than it's actually worth. But if you were to flip open a chemistry book and look at the very back where it has a whole list of delta H's, you will see that the enthalpy of formation of lithium fluoride solid is negative 617 kilojoules per mole, meaning the fact that energy is released. If we kind of go back and compare this value, 432.5 positive and 617 kilojoules negative, there's a huge missing step there. There's something that again isn't accounted for that is not only big enough to release the energy to kind of again counteract this 432.5, but it's so large that it still releases 617 more than that amount of energy is being released. So luckily for us, I kind of talked about this in the past, but didn't really give it a name. But this attraction between oppositely charged ions, or this lithium plus being attracted to your fluorine minus, or your sodium plus being attracted to your chlorine minus, or your iron 3 plus being attracted to your SO4 2 minus. This attraction of oppositely charged ions or particles or molecules, for instance, not molecules, sorry, or polyatomic ions, they're always going to release a whole lot of energy. And so even whenever we have our lithium plus ion and your fluorine minus ion in the gaseous state to give you your lithium fluoride gas, it's going to release 755 kilojoules of energy. And as you can kind of tell, that negative 755 kilojoules of energy is more than enough to satisfy and to kind of, again, counteract that 432.5 that it costs to set everything up. But lithium fluoride doesn't normally exist as a gas. And so the way it technically exists is as a solid. And so going from the gaseous lithium fluoride to a solid lithium fluoride, or remember, having these gaseous molecules and particles that bounce on all over the place, and then finally calming them down enough that you can sit them all in their nice little rows and alternating pluses and minuses, that actually releases even more energy. And so in these cases, setting everything up does cost some energy. Setting everything up in order to be an Li plus and an F minus, it's going to cost some input. You have to put some energy into that system in order to get everything set up in the right form. But as soon as everything is set up in the right form, it's going to again kind of start rolling, and it's going to release a whole lot more energy than you had to put into it. And so again, going back to my analogy of the money, if you put in $500, again, a lot of money for us, but in order to get paid back more than double that amount of money is way worth it in terms of, again, energy, in terms of money as well. And so this last step here, or that lithium plus the fluorine minus becoming lithium fluoride. The reason why I specifically put the gas and the solid and everywhere where I did is because this leads us into the definition of what we refer to as lattice energy. And so, one thing you have to notice about lattice energy, and why I put it in big red bold letters here, is the lattice energy is technically the negative of the enthalpy change that I talked about on the previous slide. And so on the previous slide, I have lithium plus gas plus F minus gas gives you lithium fluoride solid. And the delta H associated with that is going to be your negative 1050 kilojoules of energy. And so negative of that, or your positive 1050 kilojoules of energy, is just going to basically, again, flip that arrow around. And so now you're looking at the lithium fluoride solid becoming lithium ion gas plus fluorine ion gas. That's not really an important part. The main thing you have to understand, and again, why I put it in a completely different color than everything else on the slide, is you have to understand that this lattice energy is always going to be between a solid ionic compound turning into gaseous ions. And so please note those two characteristics are a must. You have to have a solid ionic compound, and it has to split up into gaseous ions. And so if you have something that is not an ionic solid, and if it doesn't split up into gaseous ions, then you're not looking at lattice energy. But once you know that, again, flip the sign around. If it's given to me positive or negative, that's not the main issue here. And so all of these last couple slides can be summed up into what is referred to as the Born-Haber cycle. And so I understand that Born-Haber cycle looks insane, it looks scary, and if you looked at your book too early, it probably freaked you out and made you close your book. But the whole idea is that it is nothing more than these previous steps that I talked about, these previous slides, just kind of put into a picture form. And so one thing you have to kind of understand is that I guess there's two different paths we can kind of take here. And so the first path that I'm going to talk about is going to be, again, the black arrow. That's going to be the delta H of formation, or the standard delta H of formation. And so the main thing here is this is all we as humans witness whenever we take lithium and mix it with fluorine, we see lithium fluoride. And again, if you do this inside of a particular instrument, it will say, hey, it took this much energy to do that. But as an electron, we actually will go through a multi-step path. And so that's going to be the orange, and that's going to be kind of the path I'm going to walk you through here. And so we have to revisit Hess's law. Because remember, Hess's law states that it doesn't really matter how you get to that endpoint. As long as you kind of take all the appropriate steps, you can go through each individual step, or you can take a giant leap and skip over all of them. But it just means that there is no really matter or difference depending on how you get there. And so when we kind of go through and look at these, this is what the Born-Haber cycle looks like without all that other stuff that your book kind of throws in there to begin with. And so the first kind of spot we're going to start off with is right here. And so when we talk about this step right here, notice again, it's not too horrible in terms of energy. It's less than halfway up. But again, this lithium fluoride solid is looking pretty nice because it's a lot lower in energy. And so this first part here is going to represent whenever we have our lithium solid and our F2 gas. And so the reason why it's set up here is because we're only looking at 1 mole of our lithium fluoride. And so it's going to be our lithium solid plus half of an F2, or half a mole of F2 gas, to give us that 1 mole of F. And so this black arrow, or this enthalpy of formation, is again basically what you see whenever you do this chemical reaction inside the lab. But according to my last couple slides that I talked about, This doesn't happen in a one-step process, especially if you're an electron bouncing all over the place. And so this first gap, or again, going in between this first bar right here up to this second bar, is whenever we're actually taking our lithium solid, and please note, every single one of these atoms has an atom sitting next to it. There's really no room to shove in your F in order to make your lithium fluoride. And so the first step is going to take our lithium solid and we're going to beat it and smash it and heat it up and shake it as much as we can in order to get all of these atoms to completely separate into our lithium gas. And so here, going from lithium solid into lithium gas is going to require some energy. And again, you can kind of see this by the fact that we're going up in energy. Remember, our long-term goal was to go down. But as you can kind of see, we have to put in a little bit of energy to set things up in order to kind of have this final overall release. And so the next step is to, again, take our F2 as a gas. We don't, and so we don't want this F2 as a gas. We want it to be individual Fs. And so here again, we're going to have to take half of our F2. We're going to have to take this molecule of F2 and break this bond between it, and break that bond, and break that bond, and break that bond, and break that bond, in order to get a bunch of individual Fs. And so in this case, you're going to have to take the bond energy of your F2, and we'll tell you the amount of energy required to kind of split these things up. And so at this step right here, this bond right here, we're looking at Li's and F's. But again, in order for an ionic reaction to occur, we need to have ions. And so we need to take this lithium as a lithium atom, we need to take or make it into an ion. And so here we're going to take our lithium and we're going to rip an electron off of it. And so here, in order to go from our lithium atoms in order to our lithium plus ions, we have to remove an electron. And again, ionization energy relatively for lithium is pretty small compared to the rest of the periodic table. But you have to remember and understand that it still costs energy in order for that thing to happen. And so now we're looking at our lithium plus and our F's. And so in order to convert our F atom into our F ions, again, we're going to have to add an electron. And so one thing I want to point out first before we move on any further, we started off here. This is where we are at lithium solid and F2 gas. We are now all the way the heck up here. We wanted to be down there, but right now, again, we're kind of set up that we are putting in way more energy. Again, going from this spot up to that point, we had to put in a lot of energy to kind of get things set up. But so the first payoff is whenever we actually add this electron to our F atom. And so here, once you have the electron that you took off of lithium and we shove it on the fluorine, this is the first positive sign that we see, the first release of energy. But even at this point, we started off at this bar, we now are up at this bar. And so here again, it looks like it cost more energy than this thing was worth in order to get everything set up. But luckily for us and for lithium fluoride, this last step of lithium plus ion and the fluorine minus ion, that attraction between the two is so magnificent that as soon as they come close to each other and become a solid, it releases a whole lot of energy. And so this is what we call the lattice energy. Please notice here it's actually the negative of the lattice of energy because by definition, lattice energy would be going from solid up to these gaseous ions. But if you know this value, switch the sign in front of it and you know that value as well. And so if you didn't look at all this stuff individually, this is what you saw when you looked at your book and it probably scared you a little bit. And so when we kind of go through and look at these things, the Born-Haber cycle can actually be applied to any ionic complex. It is not specifically for lithium fluoride or for sodium chloride. It can be used for like iron 3 sulfate as well. It's just the whole idea is for some of these things, you're going to have to convert them from solids to gases. Once there is gaseous atoms, you need to convert them into gaseous ions. Once you have your two oppositely charged gaseous ions, that's where the whole moneymaker is. That's when all the release of energy actually comes around. But you have to put some energy into the system in order to get things set up appropriately. And so, The next portion here is basically going to be talking about some type of energy that is very, very closely related to lattice energy. And so lattice energy is, again, going to be the energy required for you to completely separate 1 mole of ionic solid into gaseous ions. And so electrostatic energy is the attraction between your electrons and your protons. And so when we start talking about putting these things into complexes, so again, remember, electrostatic energy inside of just an atom by itself is just the attraction of those electrons to that atom's protons. But when we start putting these things in complexes, or more than one atoms, now you actually have electrons in atom A are being attracted to the protons in atom B. And then protons in atom B and protons in atom A are repelling each other. Electrons in A and electrons in B are repelling each other. There's a lot of crazy stuff going on. And so Coulomb's law states that the electrostatic energy between these particles is 1, directly proportional to their charges, the product of their charges, and 2, inversely proportional to the distance between them. And so when we kind of talk about this stuff, lattice energy, electrostatic energy, a lot of the times they're going to be used interchangeably. And the main reason for that is because both of them have the same relationships. And so whenever I say directly proportional to the product of their charges, what I mean by that is if you have something that has a +1 ion attracted to a -1 ion, those are going to have a pretty decent attraction. But if you have some ion charge that is -5 being attracted to a +5, that is going to be a much, much, much stronger attraction. And so the easiest way I can kind of describe this is if you have 2 refrigerator magnets, you can kind of stick them to one each other and you can kind of generally pull them off very easily. But if you have 2 electromagnets kind of attracted to each other, you usually don't want to get any body part in between those because it takes a lot of energy to pry those 2 magnets apart from one another. So the larger the magnetic attraction, or the larger the pluses and the minuses, the more difficult it's going to be in order for you to separate those 2 atoms. On the other side is if you have large atoms versus small atoms. Smaller atoms can get closer to one another, and so these electrons on A can be closer to the protons in B, and the electrons in B can be closer to the electrons in A, and so on and so forth. But the smaller the atoms are, the closer they can be to each other. The larger the atoms are, the further away the electrons and the protons are going to be. Therefore, it makes it a lot easier for you to destroy a long bond than a shorter bond. And so in these cases, larger charges are going to be more beneficial. Smaller atoms are going to be more beneficial in terms of how strong these things are going to attract one another. And so when we start talking about lattice energy, again, it's going to be affected by both the size and the charge. But as the size increases, your lattice energy is going to decrease because these atoms are already far enough away from each other. It's going to be easier for you to break that bond. Whereas on the other side, as your charge increases, your lattice energy increases. Because the larger a charge, the more, more intact they want to remain. And so when we kind of go through and start talking about these ionic compounds, again, this portion is not really in your book very much detail, but it's beneficial to know about. And so when we talk about ionic compounds, one thing you should hopefully by now be aware of is you can't really dent a piece of salt. If you hit a piece of salt with a hammer, it breaks. There's no kind of denting it or anything like that. And so in physical behavior of all ionic compounds is they're typically going to be hard and rigid. And so by hard, I mean you can't dent it. By rigid, I mean it doesn't really bend. If you kind of do any force, they break. And so if you've ever hit a piece of salt with a hammer, or even your hands or anything else, you notice it, again, doesn't bend, doesn't dent, it just kind of breaks into pieces. And the reason for that is because in ionic solids, these things are set up in a very specific arrangement, in a very nice, stable order of positive, negative, positive, negative, positive, negative, so on and so forth. And so if you try to hit these things and try to put them out of order, you're going to have some resistance, because again, if you try to dent it, then you're trying to force this positive atom next to that positive atom. Or you're trying to force this negative atom, or sorry, ions, this negative ion next to that negative ion and that negative, and it just doesn't work out very well. And so the only thing that ionic compounds can do is if you put extreme force on it, again, if you smash it hard enough in order to kind of break it along this line, and now you have positive sitting next to a positive and negative next to a negative and a positive next to a negative, those things will immediately repel each other. And that is actually what leads to cracks in these ionic complexes. And so again, if you can put enough force on this structure in order to, again, force these things to align as positive and positive, Mother Nature will do its job and kind of make these alignments, well, unaligned. And so essentially, again, all these cracks are going to be along a position where you have this negative sitting next to a positive and positive next to a positive. So they don't always have to be perfectly straight lines, but again, they're going to always be along the line where this force is actually kind of making the alignment almost impossible to maintain. And so another kind of complex or idea that we can talk about with ionic complexes is conductivity. And so I have stated ever since around chapter 4 or so that ionic complexes do or are electrolytes. They do conduct electricity. So one caveat that I didn't really think to mention in that chapter, mainly because we were talking about aqueous chemistry, is these ionic salts are only going to be electrolytes when they are in solution or when they are molten. And so please do not have the misconception that you can conduct electricity with solid salt. It will not work out that way. And so in order for you to actually have ability to conduct electricity, you need to have ions that are mobile. And so in these cases, molten salts or dissolved salts, those are going to be perfect or great electrolytes. And so by molten salt, I mean that you have heated it up enough so that these ions are no longer in their fixed plus minus fixed position. And so in these cases, once you have these things heated up enough, or if you kind of throw them into water and they're soluble in water, then these are going to be able to conduct electricity. And the last thing we kind of have to talk about in terms of these ionic salts is the property of melting and boiling points. And so if you've ever kind of thought about it, and again, please note here, I'm not talking about in solution, I'm talking about the actual compound itself. But if you've ever kind of considered the fact that these pluses and minuses line themselves up very, very nicely in order to have the energy minimized, meaning the fact that they are very stable. Your table salt is not just going to spontaneously break down into sodiums and chlorines. It's probably going to stay nice, stable table salt until you either eat it. And again, if you just left it there for 100 years, it's not going to kind of go back the other way. It's going to stay table salt. And so the reason why it's very stable is because this plus-minus situation kind of distributes stability throughout the entire complex. And so they have very, very high melting points and even higher boiling points because you have to put a lot of energy into that system in order to break up that nice arrangement of pluses and minuses everywhere. And so it's so much energy that even whenever these things are vaporized, they still tend to exist in these what they call ionic pairs. And so there is, again, it doesn't happen too often in any McDonald's, but you can have lithium or sodium chloride gas exist, mainly again because they're not in their solid form. And so the other half of this chapter is going to be focusing on covalent bonds. And so when we kind of talk about your covalent bonds, remember, we are now talking about electrons being shared, not being transferred, but being completely shared. And so when we kind of talk about these things, when you use your Lewis symbols, we kind of transfer our dots into lines in order to illustrate these things are being shared between them. And so anytime that, again, you have two dots in between two atoms and those two dots are being shared between both of the atoms, you can represent this by a line. Now this line, again, does not really exist. There is no such thing as a line between atoms when we talk about these chemical formulas and chemical structures. It is the way that we depict these electrons being shared, or how these how these orbitals are actually going to start overlapping, which we'll revisit in chapter 11. So you may have heard the terms of single bonds and double bonds, and if you talk to anybody in the chemistry world, then triple bonds. But the whole idea here is that you cannot really think about these bonds as lines or as, again, sticks in between these atoms. And the main reason why I warn you about this now is because it comes up again in chapters 10 and 11. And so if you start picturing these things as the ball and stick models, that's fine, but you just have to remember that each of these lines is the same exact thing as the previous line. And so whenever I talk about a single bond, I'm talking about two electrons being shared between those two atoms. But whenever I talk about something like a double bond, or what they refer to as a bond order of 2, I am not talking about anything special. A double bond is not any more special than a single bond. A double bond is nothing more than the fact that there are 4 electrons being shared between the atoms instead of 2. And so when we start talking about, again, later on in chapters 10 and 11, when I start talking about pi bonds and, again, these sigma bonds, you have to understand the same bonding structure, the same 2 electrons per bond still exists. And so when we talk about single bond, double bond, triple bond, or bond order of 1, bond order of 2, bond order of 3, that is nothing more than just the number of electrons being shared between these atoms. All it's really saying is that those 2 electrons will form 1 bond, or 2 electrons per bond. And so the bond energy is the average amount of energy required for you to destroy that bond. And so when we kind of talk about these things, higher the bond energy means that there's a stronger bond. And so one thing you have to understand and kind of appreciate is, as I've been talking about in the previous couple slides here, bond formation is a good thing. Lithium fluoride, the whole reason for lithium solid and fluorine gas to even interact and join one another is to release energy. And so a release of energy is going to be an exothermic reaction, which is, if you are an atom or an electron, exothermic reaction is a good thing. That's what we want. But bond breakage, that is the complete opposite of bond formation. So bond breakage is always going to be an endothermic reaction. You always have to absorb energy in order to break a bond. And so the easiest way I can kind of relate this is, if you have a stick, that stick is not going to just break just because you want it to break and you stare at it really hard. You actually have to put energy into that stick in order to bend it, in order to snap it in half. And so in these cases, again, bond breakage is an endothermic reaction requiring energy from an outside source. Bond formation is an exothermic reaction, which again typically is a good thing if you're an atom. And so when we kind of go through and start talking about all this stuff, sorry, my screen kind of changed here. Went out of presentation mode. Sorry. Whenever you go through and start looking at these things, the bond length, the way that they measure this, it's kind of empirical. Mainly because, or sorry, not empirical, computational. And the reason for that is because these lines don't exist. These atoms being drawn the way I have them right here, like this, that's not real. And so when we talk about these things, the easiest way that scientists can measure these bond lengths is if you have a diatomic atom, diatomic molecule. And so if a diatomic, in this case, if you have something like Cl2, you can actually find the nucleus of these atoms. And so nuclei, those things exist. That actually does truly happen. But remember, these spheres, they're representing your electron cloud. But your electron cloud is technically empty space, and so it's not really something you can truly measure. But if you can locate the nuclei of this electron of that atom and that atom, you can measure the distance between those two. And you can do the same thing with F2 and H2 and Br2 and I2 and all the other diatomics. And once you know those measurements, then again, you can start pairing up with like sodium and chlorine. If you know chlorines, you can measure sodiums and so on and so forth. So I just want to kind of give you an appreciation for the fact that this stuff on this screen, it's all make-believe. There is no spheres, there are no lines or anything like that. So, this next table, I want you to take a deep breath before I go to it. It is not something you need to memorize. Please, dear God, do not memorize all this stuff. But the main reason why I kind of point out this table is for these highlighted reasons right here. And so one thing you should kind of notice is comparing hydrogen and iodine, just the atoms themselves. Hydrogen is excuse me, hydrogen is going to be a lot smaller than your iodine atoms. And because of that, the distance between two hydrogens is going to be much shorter than the distance between your two iodines. And so in this case, because the distance is shorter, the energy is going to be much greater. And so by that I mean the shorter bond is going to require higher energy in order to break the bond. So the easiest way I can relate this back to something that's near and dear to me, of food, but think about a piece of uncooked spaghetti. And so if you have a very long uncooked piece of spaghetti, you can snap that piece of spaghetti relatively easily by generally just breathing too hard on it. But if you have a smaller piece of spaghetti, it takes a little bit more energy for you to break that piece. And if you keep making that piece of spaghetti tinier and tinier, it requires more and more energy in order to kind of snap that piece. Or on the other side, if we look at single bonds versus double bonds versus triple bonds. And so here again, these lines are kind of misleading because whenever I say double bond, it is not really showing you that you have two single lines in there and they're not two single bonds making up a double bond. But for lack of other illustrations, we draw double bonds as two lines and triple bonds as three lines between the atoms. When we kind of go through and start looking at what this represents, is if you have two electrons between your atoms, you're only sharing those two electrons. If you have four electrons between them, you're sharing more electrons, meaning the fact it's going to require more energy to break those four electrons apart. Same deal if you're sharing 6 electrons, or if you have a triple bond, it's going to require more energy for you to separate all 6 of those electrons than it would 4 electrons than it would 2 electrons. Additionally, and again, not too extreme, but if you look at the sizes of these bonds, you'll notice that the single bond in a carbon-carbon is going to be 154, double bond is 134, and your triple bond is 121. And so in addition to you having more electrons that you have to kind of break through, you also have shorter bonds going from a single bond to a double bond to a triple bond, which from previously what I just stated, it's going to require more energy for you to break a shorter bond than a longer bond. So similar to the ionic complexes, all covalent substances have very similar properties as well. And so when we start talking about molecular complexes, you have to kind of keep in mind that these are not ions, just happen to be stuck to each other because they're positive and negative. So for covalent substances, because they are sharing these electrons, again, there's not real lines or sticks between them, but we refer to these again as bonded atoms or shared electron pairs. And so in these cases, these interactions between all these atoms are much stronger than these ionic interactions. And so therefore, again, these things are not going to be as easily separated as they are when we return, or in terms of molecular strength versus the ionic strength. And so when we kind of talk about these, there's actually kind of two different types of covalent substances that we are going to refer to or talk about. So the first one is called molecular covalent substances, and which is what we normally kind of deal with when we talk about molecules. And so in these cases, again, strong interactions between all the atoms. But one thing I have to point out is that there are not strong interactions between each of the molecules. And so if we have something like water, H2O, the attraction is between the oxygen and the two hydrogens. The attraction is not particularly between each of the individual water molecules. Same deal with a sample of carbon dioxide gas. And so the carbon dioxide is going to be the CO2. The interaction is mainly going to be between that carbon and the two oxygens. It's not really going to be too extreme between each of the CO2 molecules. And so that's what I refer to whenever, or what I mean whenever I refer to these as molecular covalent substances. On the other end, we have these network covalent substances. And so these are, again, still going to be your nonmetal attached to a nonmetal. They're still going to be sharing electrons. But the way that they orientate themselves gives them a lot more, I guess, rigidness and a lot more like rugged than they're going to be in sort of like the molecular form. And so when we talk about these, technically the only real true examples I can talk about is a perfect diamond. And so in other ones, again, they're going to be kind of any types of covalent complex that gives a very, very unique structure to these overall substances. And so when we kind of talk about this, diamond is one of the main, I guess, essential ideas here, and the fact that all these electrons are going to be kind of, again, orientated around each one of these atoms very specifically in very rigid structures and very unique and characteristic angles here. And so one of the last things we have to kind of talk about in terms of this is, again, going to be conductivity. And so easy here is there really is none. Because as I kind of mentioned, in order to have something classified as an electrolyte, you need to have ions that are mobile. And so if you don't have any mobile electrons, then there's not going to be any electricity that can be moved. And so far we've talked about how to put all these bonds together and what it kind of takes in order to break them. But whenever we kind of talk about these things, a chemical reaction is usually how all this stuff kind of comes together or breaks apart. And so when we kind of start talking about chemical reactions, the enthalpy of a chemical reaction is always going to be kind of composed of how much energy is required to form these bonds and how much energy is required to break these bonds. And so, as I've kind of stated in the past, some of this kind of comes down to the sign convention. And so, as I've kind of stated in the past multiple times, is bonds being broken is going to be an endothermic reaction, meaning it has to require energy from an outside source. And so even though I have it written in red, again, it's going to be a positive number. On the other side, bond formation is going to be an exothermic reaction, and it's going to be a negative value. And so here, that's the main thing you have to pay attention to. It's a simple addition problem, but if you have the wrong positive and negative values, things will kind of go downhill very quickly. And so, in an exothermic reaction, it just means that your negative value is going to be greater than your positive value. Or again, energy is going to be released. The only way you can have energy being released is if the bond formation is greater than the energy required for bonds being broken. And the same for the other end of things. And for an endothermic reaction, your bond breakage has to be greater than your bond forms. And so here again, energy is going to be required or has to be absorbed in order for this reaction to occur. And so when we kind of look at these things, again, generally only certain bonds break and form. But luckily for us, using Hess's law, we can break and form whatever we want as long as we end up with the correct answer. And so in these steps, and again, I have two examples here to kind of show you, to walk through these steps. But when it kind of comes down to it, the first thing you're going to do is break all the bonds of your reactants. First, figure out what's connected, and then just break them. And so generally for these types of problems, you'll be given bond energy. So the main thing you have to remember is bond breakage is going to be an endothermic reaction, so you need to have a positive value for these. And so once you break all these bonds, you're going to have what I'm going to call free atoms. And so now you have free atoms. In order to form your products, you need to stick those atoms with the respective other atoms, or you need to form bonds between them. And so again, bond formation is going to be an exothermic reaction, or your delta H or your values, your bond energies need to be negative. And so once you know the amount of energy required to break your bonds and the amount of energy that's released whenever you form your bonds, you add them with the appropriate signs in order to get the delta H of your reaction. So, for example, if we are looking at the, again, combination of H2 plus F2 to give us two HFs. And so here I'm telling you that the bond formation, bond energy for your HH and your FF, and I also tell you the bond energy for your HFs. And so here you just need to figure out how much energy is required to break this bond, to break that bond, and to form two brand new bonds. And so here, as I kind of stated, you just have to make sure that your sign convention follows through, and everything else is just a bunch of addition problems. And so as you can kind of see here, in order to break your H2 bond, it's going to require 432 kilojoules of energy. And because we only have 1 mole of that stuff, we know that 432 kilojoules of energy must be absorbed in order to break this 1 mole of hydrogen, or HH or H2 bond. Additionally, we have our F2 bond, which is going to require 159 kilojoules of energy absorbed in order to break this 1 mole of FF. And so, when we kind of go through and look at these, in order to break both of these bonds, we're going to have 591 kilojoules of energy absorbed in order to break both of these bonds. But as soon as both of those bonds are broken, we can move up to where I have those free atoms, and now we have two H's and two F's just kind of roaming around waiting for things to happen. And so now we need to reattach those with the respective atoms in order to give us our HF. And so on the other side of the screen, I have the fact that bond energy for each of these is 565 kilojoules per mole. But as I kind of stated in the previous slides, bond energy by definition is the amount of energy required to break these bonds. And so if we want to know the amount of energy required to form these bonds, we just need to change the sign in front of that. And so here, 565 kilojoules of energy is going to be released, not absorbed, but released when 1 mole of your HF bond is formed. But as you can kind of see here, or if you were to write out the balanced chemical equation, we're actually forming 2 of these complexes, or we're forming 2 moles of your HF. And so in order to make everything kind of line up properly, 2 times the negative 565 will give us negative 1130 kilojoules of energy. And so remember, the only reason why it's negative is because this energy is being released. And so when you add these values, just make sure that your bonds being broken is going to be a positive value, and your bonds being formed are going to be a negative value, and add them together. And so here, the delta H, or the standard delta H of this reaction, is negative 539 kilojoules of energy, implying that this is an exothermic reaction. And so if we look at another example of CH4, and so the combustion of CH4 requires a CH4 and oxygen molecules. And so here, because we have CH4, you have to remember that there are 4 bonds in that CH4. There is, again, 1 central carbon and 4 hydrogens surrounding that. And so we're not just looking at 1 bond being broken, we're looking at 4 carbon, hydrogen, carbon, hydrogen, carbon, hydrogen, carbon, hydrogen. We're looking at 4 bonds total. Each of those bonds has a bond energy of 413 kilojoules per mole. Similarly, whenever we look at the oxygen, and I just now realized, this should be an oxygen-oxygen double bond right there. But whenever we kind of look at this, our oxygen, since we have 2 oxygens, we're going to need to break 2 oxygen-oxygen double bonds. And so just keeping your numbers lined up, and again, using the given bond energies, in order to break all of our carbon-hydrogen bonds, we're going to need to absorb 1652 kilojoules of energy. In order to break both of our oxygen-oxygen double bonds, we are going to require 996 kilojoules of energy. And so one thing I need to point out here is the bond energy given to you in this problem for your oxygen-oxygen bond is 498 kilojoules per every double bond. And so this is why I tried to point out previously that that double bond is just a word. Please do not think of it as 2 single bonds, because it is not. And so in this case, you would not multiply that number by 2 and then multiply by 2 again, because that 498 kilojoules of energy is the energy required for you to completely break that oxygen-oxygen double bond. And so please just use the value they give you and do not manipulate it any further than that. And so once we, again, have both of these values calculated, we know that it's going to cost us a total of 2648 kilojoules of energy to break all 6 of those bonds that I have highlighted there. But once we break them, now we have a bunch of free bonds, and so we need to go to the other side of the screen. And so here you can see that I need to form CO2 and 2H2O. But as I stated previously, that CO2 has 2 carbon-oxygen double bonds that need to be formed. It also, on the other end, has 4 oxygen-hydrogen bonds that need to be formed from your 2H2O. And so for these, again, you have 2 carbon-oxygen double bonds and 4 oxygen-hydrogen bonds that need to be formed. And so just keeping track of the number of bonds using the given bond energies, you can see that for your carbon-oxygen bonds to be formed, both of them, is going to release 1598 kilojoules of energy. And the same deal with all 4 of your oxygen-hydrogen bonds being formed will release 1868 kilojoules of energy. Or again, a total of negative 3466 kilojoules of energy for your delta H of energy being formed. Keeping your positive and negatives lined up, then you can see if you add them together, you have an overall standard enthalpy of reaction of 818 kilojoules of energy being released. Or a delta H of reaction is going to be negative 818 kilojoules of energy. And again, this should make sense because combustion of CH4 is whenever you burn your methane. And again, if you've ever been close to fire, it's hot. You feel energy being released. So the remainder of this chapter deals with what we refer to as covalent bonds. And so I need to make something perfectly clear at this point, in the fact that pure ionic substances do occur. And so anything that you have a positive ion and a negative ion, those are referred to as ionic compounds, plain and simple. But when we talk about covalent bonds, there's a little bit more of a wider spectrum that you can refer to as a covalent bond. And so a pure covalent bond only exists in diatomic molecules. And so polar covalent bonds are basically everything else that is not 100% ionic or 100% covalent. And so in this instance, whenever I'm talking about polar bonds, all I really mean is the fact that there is not an equal sharing of electrons between these things. And so remember, ionic bonds, there are 100% transfer of electrons. One electron goes from a sodium to a chlorine. But when you start talking about covalent bonds, something like Cl2, it's easy to see that chlorine 1 has the same attraction, same bond energy, same atomic size, everything as the other chlorine. And so in something like Cl2, there is no real fight for these electrons because they have an equal attraction between the two. But if you have something like HCl, for example, there is a difference in electronegativity, a difference in ionization energy, a difference in electron affinity between hydrogen and chlorine. And so in that instance, there's not going to be an equal attraction of electrons between hydrogen and chlorine. And so because of that, we cannot call this pure covalent because there's going to be an unequal sharing of electrons between the two atoms. And so when we kind of go through and start talking about this whole idea of electronegativity, it is nothing more than the ability of an atom to attract shared electrons more strongly than its other atom. For instance, going back and talking about HCl, chlorine is going to be way more electronegative than hydrogen. And because of that, it's going to be much more willing to steal some of that electron power away from hydrogen. And so in this case, and again, the values are on the next slide, so don't panic yet. But when we kind of talk about something like HF, fluorine is the most electronegative atom. In that case, it's going to attract more of hydrogen's electron than even hydrogen is going to. And so here you can kind of think about it as fluorine is kind of stealing the hydrogen's electron more than really sharing it equally. And so the way I can kind of describe this is imagine that again, hydrogen comes up to fluorine and says, hey, I have one cookie, I will share it with you. And fluorine is being stingy, and it has 7 cookies, but it hides 6 of them from hydrogen and says, sure, I'll share my one cookie with you. And so fluorine, not only is it sharing hydrogen's cookie, it takes a larger bite out of hydrogen's cookie than it really should have. And so here, there's an unequal sharing of cookies. And so fluorine is being stingy, and it has way more access or way more attraction to all these shared electrons than hydrogen does. Because of that, that just means that fluorine is going to have not only its unshared electrons, but it's also going to have more of hydrogen's shared electrons than hydrogen does. And so we kind of go through and start looking at these. Electronegativity, for some reason, I don't know what Pauling's issue was, but electronegativity is going to be measured up to a value of 4.0. And so you just really need to remember the general trend, and again, we'll kind of help you out here. But general trend for this is fluorine is going to be the most electronegative atom. That is something that will never ever change. So fluorine is going to be the most electronegative atom with a value of 4.0. Cesium and francium are going to be the least electronegative atoms, and they're going to have a value of 0.7. And so again, there is really no 0 on the scale. And again, highest it goes is 4.0. Another way to kind of help you out in figuring this out is it's basically the exact opposite trend of the atomic size. So nonmetals are going to always be more electronegative than metals because they're always going to have a stronger attraction to electrons than your metals are going to be. And so remember, metals always make positive charges or positive ions. So they're essentially saying, I don't like my electrons so much, I definitely don't want your electrons. And so we kind of look at this blown up screen here. And please note, the transition metals, they're kind of screwy. I won't ask about any of those. But in general, again, fluorine is all the way up there at 4.0, going all the way down kind of diagonally. So going from fluorine diagonally down to francium, you go from 4.0 down to 0.7. I will never ask you for, well, maybe francium and fluorine, or for all the other values, I will not ask you for an exact value. But what I will do is expect you to know the general trend when you kind of go through and look at these. And another point that I kind of talked about is the fact that it is generally the exact opposite of your atomic size. And so as you can see, fluorine is one of the smaller atoms, again, out of the main group elements, and so therefore it's going to be more electronegative. And this whole idea can be kind of associated with the fact that fluorine's electrons are going to be much closer to the nucleus than cesium's electrons. And because they're going to be much closer, and again, fluorine is going to be a much smaller atom, it will actually attract other electrons much higher than any of the other metals will. So, next thing I did is we have to kind of go visit or revisit our oxidation numbers. And so when I first kind of introduced these oxidation numbers in a previous chapter, I kind of just told you, hey, memorize these, and then you kind of just went about your life. But now, here's the reason and the way that these oxidation numbers were actually developed. And so one thing I have to point out here, and again, if you do not listen to me now, then you'll go back and rewind it until this point, because you need to pay attention to your electronegative atoms. Because the most electronegative atom will be assigned all of the shared electrons. The least electronegative atom gets none of the shared electrons. And so in this instance, it's kind of going back to what I was telling you before, is electronegative atoms will steal more of the electron from the shared atom than it normally does. And so once you kind of establish the fact of what is being shared and what is not being shared, then you can use this equation of the oxidation number equals the number of valence electrons minus the number of shared electrons minus the number of unshared electrons. Or put them in parentheses, it's the number of shared electrons plus unshared electrons. And so when we kind of go through and look at this, let's check out HCl here. And so when we kind of go through and look at this, you have to look at, again, use both of those equations, or that previous equation, for both of these atoms. And so the first thing you should kind of notice with this electron-dot structure is chlorine has 6 unshared electrons. Hydrogen has no unshared electrons. and between the two electrons are being shared, or there is one bond. And so going through and just checking out the information about chlorine. So here, chlorine is going to be the more electronegative atom than hydrogen. And so we know for chlorine, there's a few things we can determine. First off, even if you don't have a periodic table handy, you know that we have 6 lone pairs, and so therefore one of those electrons has to be kind of being shared. And so valence electrons, chlorine has 7. When we talk about shared electrons, again, we're talking about how many electrons is it sharing with hydrogen. And as I mentioned on the previous slide, if you don't remember this one rule, you're going to mess up. But chlorine is the most electronegative atom, so it gets all of the shared electrons. And so one bond is 2 electrons, and so chlorine gets both of those shared electrons. And again, this just happens when you're calculating oxidation numbers. And the last one is unshared electrons, or how many dots do you have surrounding this atom. And so here unshared electrons would be 6 because you have 6 dots. And so your oxidation number is going to equal your valence electrons minus your shared plus unshared. Or in this instance, your 7 minus your 2 plus 6, or an oxidation number of -1. Luckily for us, this is what I told you way back when you still saw my beautiful face, what the oxidation number of chlorine is supposed to be. And on the other end, let's check out hydrogen. And so hydrogen is the least electronegative number. And so here, valence electrons, it's in group 1, it's always going to be a 1, and so we know we have 1 valence electron for hydrogen. Now, shared electrons. This is where a lot of you are going to run into issues if you didn't listen to all my previous warnings. And so, because hydrogen is the less electronegative atom, it gets none of the shared electrons. And so here, shared electrons for hydrogen gets 0 of those electrons. All of the shared electrons went to chlorine already. But as unshared electrons, even more sad about hydrogen is it doesn't have any dots. And so therefore, it has 0 unshared electrons. And so using that same equation, we have our oxidation number equals valence minus shared plus unshared. We have 1 minus 0 plus 0, or a +1. Or again, as I mentioned several times in the past, the oxidation number and the ionic charge of hydrogen is going to be a +1. And so, when it comes to writing these things out, most of the time you would not really want to write out all this information about hydrogen and chlorine. And so we can typically write these things out using either what we refer to as polar arrows, or we can use what we refer to as partial charges. And so polar arrows is nothing more than an arrow with a cross for a butt. And so here, your cross for the butt will always be wherever your positive charge is going to be, or in this case, it's going to be pointing towards the more electronegative atom. Or in this case, again, you can refer to these as partial positive and partial negative in order to kind of illustrate the fact that chlorine is being greedy and stealing some of hydrogen's electron. Because some of the electron is being stolen from hydrogen, it's going to be partially positive and partially negative. So one thing I have to point out about these partially negative and partially positive charges is we call them partially positive and negative because they are not ions. Hydrogen has not completely lost its electron. It still has it. It can still see it. It's just a lot closer to chlorine than it is to hydrogen. It is still being shared. It's just being shared completely unequal. And so then in this case, you'll never see these partial charges on ions because they are either positive or they are negative. There is no gray area for ions. But for molecules, if you do not have an equal amount of sharing, or again, the only time that happens is between diatomic molecules, you have a partial charge on one of those atoms that is, again, losing some of its electron density. You're going to have a partial negative on the atom that is stealing some of that electronegativity or stealing some of that electron density. And so, one way we kind of talk about how polar something is we use the electronegativities and calculate what they refer to as the electronegativity difference. And all that really means is subtract the two numbers. The greater the difference in their electronegativities, the greater the polarity of the bond. And so in diatomic elements, you're going to always have an electronegative difference of 0. because if you're subtracting two of the same numbers, that's the only way it can ever happen. And that is why we refer to these as purely covalent. Anytime you have a delta or delta En or electronegativity difference of 0, it means you're looking at something that has the exact same attraction and repulsion, for that fact, of these atoms. And so it's not going to, again, be anything shared unequally.